As you may have heard, Steven Weinberg died recently, and so I was thinking about doing a video about him, and I decided to do one on Steven Weinberg's bad Nobel Prize. Now, to begin with, I admired him. One of the reasons or a couple of the reasons I went to the University of Texas to study physics was because Weinberg and Wheeler were there, and I thought that being two of the great physics minds of their time, that perhaps I could learn something from them. Although they didn't really interact with undergrads, and even later Weinberg wouldn't correspond with me on any of my issues or anything I wanted to discuss. But that aside, he was busy. But the thing that is interesting about him in particular is that he's one of several scientists who received a Nobel Prize for a nonsense physics idea, fictitious physics. And that's not to say that the Nobel Prize committee is at fault. They only follow what they're told. And it's frequent in physics that the last person that discovers something gets the credit, like Röntgen or Marconi. And sometimes someone has an idea that becomes obsolete, like Yukawa. And sometimes someone just comes up with an idea that's total nonsense, like Gelman and Weinberg. And sometimes there's theories that are great, like Planck and van der Waals, or discovery like Carl Anderson discovering the positron that should still be celebrated. So many of the Nobel Prizes are good. In the case of Weinberg, he received his prize for the electroweak theory. In particular, the W and Z bosons, or Z for my English friends. These bosons were the solution for how a quark is converted to an electron when you change from, say, a neutron to a proton during decay, or neutron decay or beta decay. Now, the most fundamental flaw in this is it violates the principle of conservation of energy. You can't get an 80 or 90 GeV particle from a particle with a mass of less than 1 GeV. This is a violation of the principle of conservation of energy. Right there, this theory should have not moved forward at all. It should have been dead. And even the idea that an up quark can transform to a down quark with a mass twice as much without any source of energy, that's a violation of conservation of energy as well. So it should have been a dead theory, and it should not be accepted. Now, the other part of that is, in order to avoid the conservation of energy problem, you could say, well, it's a quantum fluctuation. But quantum fluctuations are limited in time. d dt equals h bar, or h bar over 2, depending on how you're accounting for the total energy. So the problem there is that the time it exists only allows it to travel 10 to the minus 17 meters, approximately. While a proton is almost 2 times 10 to the minus 15 meters, depending on what you accept as the proton charge radius. In my calculation, it's 0.925. So basically, you have this huge proton, and you have supposedly a quark emitting a W boson that moves this far inside the proton and then converts to an electron. So the electron is still inside the proton and never leaves. So it can't work. So even if you have a quantum fluctuation that you think doesn't violate the principle of conservation of energy, it can't do the job. And then the third part of the conservation issue is conservation of other things. Because in quantum field theory, it's normally considered that quantum fluctuations come in pairs, particle pairs. And the reason for that's very simple, is you want to have a positive and negative of properties that are conserved so that you have a net zero. So you have matter and antimatter, which annihilate, leaving zero. You have positive and negative charge, which annihilate, leaving zero. Positive and negative magnetic moment, which equals zero in that. Positive and negative spin, which is zero. And angular momentum, positive and negative, zero. So when you have a particle pair, you still have zero net energy or zero net conservation of momentum, magnetic field, magnetic charge, matter, antimatter. So you can't have a single particle be a quantum fluctuation. At least I contend that. There are physicists who'll say, oh, sure you can. But I say no, because it violates numerous conservation laws. And if you insert a WZ particle pair into Weinberg's theory, then it doesn't work at all. Now, there are even more basic problems that his theory didn't solve. Number one being, what initiates the beta decay? What causes it to start? If you study quantum field theory, you know that spontaneous emission, where an atom has an electron transition that leads to a photon being emitted, that spontaneous emission is thought to be initiated by a quantum fluctuation. And the same thing with blackbody radiation. Blackbody radiation is initiated by a quantum fluctuation interaction. But then people will go to beta decay, when an atom decays by emitting an electron or positron, and say, oh, it happens by magic. Nothing happens by magic. If your theory doesn't explain how the interaction, how the decay interaction is initiated, then you have a terrible theory. So you need something to start. And then you need to explain how this initiator causes there to be a number of different half-lives depending on the isotope. Why is there this probabilistic distribution of half-lives for even a single isotope? And then for multiple isotopes, why are they so different? And yes, a lot of that has to do with the structure of the nucleus. But you also have to have some randomized something that initiates the interaction that causes this probabilistic distribution of half-life decay. And then you also have to explain the energy decay curve. How do you get different energy electrons and positrons being emitted during beta decay? And you typically have a curve like this. I'll put up a bigger one, where you have a peak at one energy, and in neutron decay that energy is around 280 keV in one commonly cited example that I link to in the paper where it discusses. But a maximum of 782 keV, which is the extra energy required for a proton to become a neutron. You need the mass energy of the electron plus an extra 782 keV. And so the maximum beta energy curve usually reaches that. Now, to understand where that comes from, if you take the mass of a neutron minus the mass of a proton minus the mass of an electron-positron pair production event of 1.02 MeV, you get 274 keV left. which is almost exactly the peak of the neutron beta decay energy. So what we're looking at is it has to be either a photon or a quantum fluctuation, and we don't always see photons involved. So we have to have quantum fluctuations at the pair production energy causing this beta decay interaction. And that's how beta decay is initiated, with a quantum fluctuation, with the quantum fluctuation at the pair production energy being the ideal energy for this to happen. So what effectively happens is you have a positron and an electron here, where the positron interacts with the neutron-like component of the neutron, which may be, the electron-like component of the neutron, which may actually be an electron inside the proton. And then it leaves an electron outside. And by being at this energy, it's a simple matter to produce an electron with the energy coming from the quantum field. The excess energy is not left over in a neutrino. The energy comes at front from the particles that are initiating it. You actually have to consider the energy of the quantum field. And then when you consider how a neutron forms, you have a proton-electron. Once again, you have an electron-positron quantum fluctuation, but in this time, the positron annihilates with the electron, and then the electron gets inside the proton. So this is a quantum tunneling type event, if you would, that leaves a neutron with the electron and positron, quantum positron, annihilate, leaving nothing behind. So this is a simple mechanism that allows us to have beta decay that doesn't have anything to do with W and Z theory. So quantum fluctuations initiate beta decay. And the quantum fluctuations determine the probabilistic distribution of half-lives and the energy decay curve, the energy curve of the decay products. Now you might say, well, what about the W and Z that has been identified experimentally? Well, first of all, they don't even exist long enough for us to see that they do anything. Linking those resonances with the W and Z electroweak theory is just the fallacy of wishful thinking in action. It's unscientific. And if you look at the Onium theory, and I'll link to a paper where I talk about this, we find that if you have a relativistic proton orbiting an antiproton, it has an energy of 124.86 GeV per c squared, approximately, which is essentially the Higgs boson energy, which was initially measured at 125.18. So the Higgs boson experimentally is just a relativistic proton. Then if you look at the relativistic energy of a sigma baryon, a positive one in particular, it has 81 GeV per c squared of mass energy, which is slightly more than the mass of the W boson. But there are several different ways to formulate this where you can get a closer approximation. And then a chi baryon has a mass of 90.6 GeV, which once again is close to the Z baryon, the Z boson. So when we talk about what are those resonances, we have a totally different solution that has nothing to do with the electroweak theory. It just has something to do with a relativistic baryon in orbit around another particle. So we don't have to have WZs, the experimental W and Z, being related to electroweak theory at all. And it's not. It has nothing to do with it. And the Higgs doesn't have anything to do with the Higgs theory, but that's a different bad Nobel Prize. So anyway, I hope you enjoyed this video. I still think that Weinberg was a great man in many respects. He just should never have got the acclaim that he did for his electroweak theory. And if you did like this video, please like it, share it with your physicist friends, subscribe for my next ones. I'm going to do a series on bad Nobel Prizes in addition to my fictitious physics and other videos. And then if you'd like to read about bad physics, you can read my book, The 100 Greatest Lies in Physics, where I discuss over 160 lies, and there are hundreds more, that if you actually apply logic, such as this, and apply quantum field theory, such as what are quantum fluctuations actually doing, then you get different answers than what's in the standard model in many cases. And I also have my book, The Zero-Point Universe, that builds up a physics model based on quantum field theory of the zero-point field. And my particle theory book, Goodbye Quarks, the Onium theory, where I discuss the Onium model and develop that. So if you'd like to learn a lot more about any of the physics I've discussed here, then buying one of my books may help you. And it may help me, since I'm a retired independent researcher, and every little bit helps me in my retirement. So I appreciate you watching. I hope you enjoyed it. Thanks.